We got a baby bird. The baby bird gains weight. That's a good thing because if you don't, so you don't gain weight, you don't live. So the bird has to gain its weight. So that's good. B of t is the weight of the bird, and dB dt is the rate of change of the weight of the baby bird. And we know that at its initial weigh-in, when it was t equals 0, it weighed 20 grams, and I said B is the weight at any time t days after it was first weighed. And first we want to know, is the bird gaining weight faster when it weighs 40 grams or when it weighs 70 grams? And so, well, if the rate at which it's gaining weight, we want to know if that's faster, if that's larger when it's 40 or larger when it's 70. So the rate at which it's gaining weight is dB dt. So we just need to evaluate dB dt. At b equals 40, which it was 1/5, right, of, what was it 100 minus b? So that's 60 over 5 or 12. And then we'll evaluate dB dt. That's not a d. dB dt at b equals 70 was the other one, I believe. And I got 30 over 5, which is 6. And so, well, 12 is greater than 6, and so it's gaining weight faster when it weighs 40 grams. Good or no?
Excellent.
Great. 1 point for dB dt, for using dB dt at all, and 1 point for the answer with a reason. Reason being 12 is greater than 6. All right. Part B says, find the second derivative of b with respect to d, with respect to t, and explain why this graph can't be the graph of b. So first off, let's find the second derivative. So the second derivative of b with respect to t ought to be the derivative of dB dt. Well, the derivative of dB dt is the derivative of 1/5 of 100 minus b. So the 1/5, which is a constant, will just stay. And the derivative of negative, or 100 minus b, so effectively just the derivative of negative b, is negative dB dt, because you're taking the derivative of b with respect to t. And so then we'll just rewrite this as negative 1/5 times 1/5 of 100 minus b, which is negative 1/25 of 100 minus b. And if we look at the graph, we'll note that this bird's weight is always less than 100 grams. True? Should see that. Which tells us that if b is less than 100, the second derivative should always be less than 0, because 100 minus b is going to be positive, and negative 1/25 of a positive is negative. So that tells us if the second derivative is always negative, it tells us that the graph should be concave down. But if we go back and look at the graph is clearly concave up at the beginning, and therefore it cannot resemble it. So we'll just say that's why, right? The second derivative is always negative. The graph should be concave down, but it's not. And that was worth 2 points. So 1 point for correctly getting negative 1/25 of 100 minus b, and 1 point for should be concave down, but it's not. Good. Any questions there on part B?
For these questions, are there multiple ways to justify it?
Sometimes. How'd you justify yours?
I said since the critical value is at 100 only, it can't have an inflection point before that, but it changed concavity below 100.
Yeah, sure, that'd be fine. That would work. Any other questions on part B there? All right. Part C just wants us to use separation of variables. How nice of them to tell you to separate the variables to find a particular solution. So we've got dB dt equals 1/5 of 100 minus b, and dB over 100 minus b then is 1/5 of dt. So there's your first point for separating the variables. Then we integrate. On the right-hand side, that should just be 1/5 t plus a constant. On the left-hand side, we have to do a u sub. U equals 100 minus b. If u is 100 minus b, then du is negative dB. So we put a negative inside, a negative outside. And we end up with negative natural log absolute value 100 minus b. And this is worth 1 point for getting both integrals correct, and 1 point for remembering to write plus c.
Sorry if I'm like completely missing this, but wouldn't it be easier if you like simplified out or like multiplied out the 1/5 first? Oh wait,
What do you mean
no,
multiply?
never mind.
What?
Sorry,
You're good? Oh, you just make it, yeah, if you do that, then you can't separate the variables. I mean, you can, you're gonna have 20 minus 1/5 b, but that's all in the denominator here, which makes this integral more complicated. And then you have dB over 20 minus 1/5 b equals just dt.
I
So
see.
it's fine, you get t plus a constant, but then you got the u substitution is more annoying over here. And that's a perfectly acceptable way to do it if you want to, that's fine.
I see, thank you.
Normally, though, we leave the constants on the right-hand side just because usually that, especially like in ones like these, that just makes that integral. I mean, that integral is easy to do, so having a constant attached to it doesn't make things much more complicated. But having other constants over here can be irritating. So, all right. So to get the fourth point, you need to use your initial condition, which I believe was the bird's initial weight was 20. So that gives us negative ln 80 as our constant, which gives us negative ln absolute value 100 minus b is equal to 1/5 t minus ln 80. And then we'll divide by the negative to get natural log absolute value of 100 minus b is natural log 80 minus 1/5 t. Then we'll exponentiate both sides to get absolute value of 100 minus b is equal to, well, e to the ln 80 minus 1/5 t is the same as e to the ln 80 times e to the negative 1/5 t. So we'll put the 80 from the e to the ln 80, and then e to the negative 1/5 t. And then as we take away the absolute value, we have to decide a plus or a minus here. And we can do that with our initial condition. If t is 0, this whole side is just 80. And if t is 0, b should be 20. Right? So we want this to be the positive, not the negative version of it. And so then we'll just add the b and subtract the 80 stuff. 100 minus 80 e to the negative 1/5 t. And sorry, fourth point was for getting your constant, finding your constant, and fifth point was for solving for b. Any questions there? Everyone's good? All right, trash. Let's talk about some more trash here. So we got a landfill. It's got 1,400 tons of solid waste. We got an increasing function. It tells us specifically that this function is an increasing function that models the amount of solid waste stored at the landfill. And we got a differential equation, dw dt equals 1/25 of w minus 300, that models the rate of it for the next 20 years, and blah, 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 gives us units and all that stuff. We want to use the tangent line to the graph of w at t equals 0 to approximate the amount of waste in the landfill at the end of the first 3 months. So we've seen problems where we have to use this tangent line in our differential equations quite often. So we need to use a point. What's the point we're going to use? It should be the initial condition, 0, 1,400. And then we need a slope. Our slope will come from dw dt. So we'll just plug in our initial condition of w equals 1,400 to that. So dw dt at w equals 1,400 equals, well, what was it, 1/25 of 1,400 minus 300. That's 1,100 over 25, which it would appear should go in 44 times. So there's our slope. We've got our intercept, our point. We should end up with y equals 44t plus 1,400. And they're nice enough to tell us to approximate it at t equals 1/4, not just say the first 3 months, but don't count on that. And you need to note that the units here were in years, and if we're talking 3 months, that's a quarter of a year. So we're going to approximate it at t equals 1/4. Giving us 1,411 tons of waste. And let's see, we got 1 point for finding 44 and 1 point for getting our final answer, 14. Any questions there on part A? All right, part B, another one of these second derivative ones. So we're going to find our second derivative first, and then we'll talk about what to do after that. So the second derivative should be the derivative of our first derivative. That had a constant out in front of 1/25. And then we're taking the derivative of w minus 300 with respect to t. So that's just dw dt, or 1/25 of 1/25 of w minus, what was it, 300, right? Or 1/625 of w minus 300. And then it says, so that's 1 point right there to get that. Then it says, is our tangent line approximation from part A an underestimate or an overestimate? Well, the second derivative for any w value greater than 300, and all of our w values are greater than 1,400, right? Because it says we start at 1,400 and it's always increasing. This w minus 300 is always positive, and 1/625 is always positive. So our second derivative is always positive, which tells us that our function is always concave up. Well, if we have a concave up function and we use a tangent line to approximate it, its value is somewhere along it. Well, can you tell me about the value of the tangent line anywhere other than that exact point of tangency? It's always
an underestimate.
always an underestimate, right? So I say it's an underestimate. Good or no?
Good.
No questions there on that one? All right, part C is just looking for the particular solution again. Hopefully we're getting pretty good at these. So dw over w minus 300 when you separate the variables equals 1/25th dt. So first point already, just for separating the variables there. Second point is if you integrate them both correctly. So the left-hand side, that's u equals w minus 300. And then du is just dw, so it becomes natural log absolute value w minus 300. And the right-hand side is 1/25th t. So 1 point if you got that, and a third point if you put your plus c. And it even says in the scoring guidelines, you can't get more than 2 points if you forget to write a plus c, even if you do a bunch of other stuff after that. There's 3 points, that should be pretty easy, 3 points there. And then we're going to use our initial condition that w was 1400 when t was 0. So we get natural log of 1100 as our constant. And so we'll have natural log absolute value w minus 300 equals 1/25th t plus ln 1100. And we exponentiate, we'll have absolute value w minus 300 equals 1100 e to the 1/25th t, right? Because the e to the natural log of 1100 will just become an 1100. Then we clear off the absolute value and we have to decide if we want the positive or the negative. Well, we're just going to use the positive again, because if we plug in our initial condition, we know that 1400 minus 300 is 1100. So we need this to be a positive 1100, which we only get if we don't put a negative in front of it. And then we'll add the 300 and be done. 300 plus 1100, through there. 1100 e to the 1/25th t. And fourth point for using your initial condition there, and fifth point for getting the final answer. Good or no? Questions on that one? Feeling all right about these free response with the baby bird and the trash? Baby bird trash, baby bird trash?
Yes.
Oh, good. All right. So tomorrow I'll have you guys, tonight I'll assign 2 or 3 more. I think 3 more is what I assigned to second period. So I'll do the same for you guys, that we'll go over first thing tomorrow, and then we'll kind of start changing gears, but I'll still let you guys ask questions on any of this stuff if you have any need to before the quiz on Thursday. Just a reminder, the quiz on Thursday will be 2 differential equation type problems. They will both be non-calculator. One will be like the slope field type ones, either where you have to sketch the slope field or you have to sketch a solution curve through the slope field. And the other one will be more like the baby bird trash problems. All right. So that's it for today's free response, which means now we get to move into the anti-differentiation multiple choice, which probably will take us about the rest of the period based on how it went in second period, assuming you guys have done it and have questions. So if you have questions, just type them into the chat and I will go through them in whatever order I see them first. Starting apparently with number 14. All right, 14. 14 is a good one. Requires a bit of creativity. We probably look at that and say it looks a lot like the ones where we do inverse sine, but not quite, because the inverse sine ones have a 1 minus the y squared there, or 1 minus an x squared or whatever. Well, we can easily turn that with a bit of creativity into something that has a 1 there. So we're going to write this as dy over the square root of 4 times 1 minus y squared over 4. And I just factored the 4 out of the 4 and out of the y squared. And so now this is just a square root of 4, which is just a 2 if I pull it out. So I have a 2 in the denominator. 2 in the denominator could be pulled out as a 1/2. And then I've got dy over the square root of 1 minus, and y squared over 4 is just y over 2 squared. And so now that looks just like 1 minus u squared. If I let u equal y over 2, du would be 1/2 dy. And look at that, I got a 1/2 dy. I can get rid of that constant and get rid of that dy and turn it into an integral of du over root 1 minus u squared, which is inverse sine u plus a constant, which is inverse sine y over 2 plus a constant. Good or no? All right. Next one on the list here is 32. Everyone's good there? No questions there? Okay. No, that's just people putting more questions in. All right. 32. 32. Okay. So 32 is secant of t over 2 dt. This one is this one's a little bit unfair because this is one that I'm not sure why they didn't mark this one as a BC only question. That's a little bit surprising, because you don't need to learn how to find the integral of secant and AB for anything. So this is probably their fault. But I'll tell you right now that the integral of secant x is natural log absolute value of secant x plus tangent x. For those of you taking Math 150 and 151 next year, you're going to need to know that integral eventually. And so this then just becomes a u substitution where u is equal to t over 2. So du is 1/2. So you put in your 1/2, put in your 2, and you get 2 times the integral of secant u du, which is 2 natural log absolute value secant of u, which is t over 2, plus tangent u, which is t over 2, plus your constant. And it's actually a pretty cool little trick to find this integral, just for fun. So you don't need to memorize that or know it, but just for fun. If you have the integral of secant x dx, you can turn that into the integral of secant x times secant x plus tangent x over secant x plus tangent x, and multiply by secant x plus tangent over secant x plus tangent, same thing. Then you let u equal secant x plus tangent x, And du then becomes secant x tangent x plus secant squared x. And you'll note if you distribute this through, what do you get? You get secant squared x plus secant x tangent x, which is the du. So this just ends up becoming integral of du over u, which is natural log absolute value u, natural log absolute value secant x plus tangent x plus your constant. So kind of a cool little trick there to find that integral, but not something you really need to know for this class. I'm not entirely sure why that one was included in the AB questions and not for the BC attached to it. But that's how you do it. Surprised nobody asked me about that one last period. All right, next one on the list is 52. Okay, 52 natural log root x over x dx. Just looking at that one, there's not really like a nice clean u substitution to use for it. So we got to do a little bit of creative work here again. Natural log of root x is the same as natural log of x to the 1/2, which is the same thing as 1/2 natural log x. So I could write this as 1/2 the integral of natural log x over x dx. And then I'm just going to let u equal natural log x, and then du is 1 over x dx. And we can see there's my u, and then the 1 over x dx is my du. So this just becomes 1/2 the integral of du over u, or 1/2 natural log absolute value u. Oh, sorry, that's not du over u. That's just integral of u du. That natural log is in the numerator. It becomes 1/2 of u squared over 2 plus the constant. Plus c, or natural log of x squared over 4 plus c, which is choice E. Any questions there on 52? Everybody good with 52? All right. 58 is the next one we've got here. So 58 is the integral of y minus 1 over y plus 1 dy. That one, again, requires a little bit of creativity to get through it. So one trick that we can use is we can always take the numerator and divide it by the denominator. So if we want to take y minus 1 and divide it by y plus 1, using just regular long division, this becomes a 1 up here. We subtract, we get -1 minus the 1 is -2 as our remainder. So this is 1 minus 2 over y plus 1. And that'll put it in a much easier form for us to integrate. So we just now have 1 minus 2 over y plus 1 dy. Your integral of 1 is y, and your integral of 2 over y plus 1, you should be able to do really easily. That should be minus 2 natural log absolute value y plus 1, and then plus your constant. Looks like that is choice A. Everybody good with that one? Any questions on that one? All right. Next one that someone asked for is 59. Yeah, some of these are a little more difficult than what you would expect to see on the AB test, but that's okay. We'll do this one. We got x squared plus 2x plus 2 And so we should be able to notice that that looks very close to a perfect square trinomial. And so we could rewrite this as the perfect square, x squared plus 2x plus 1 plus another 1. And then x squared plus 2x plus 1, we can factor into x plus 1 squared plus 1. And now it looks like one we should be able to use an inverse tangent on. And so if we let u equal x plus 1, du is just dx, so this just becomes the integral of du over u squared plus 1, or inverse tangent u plus a constant, which is inverse tangent at x plus 1 plus a constant, which is choice C. Any questions on that one? All right. Next one is 64. So 64, 64 requires a bit of creativity also. We might notice that if we didn't have this plus 1 up here, it'd be really easy to do a u substitution with it. So we could rewrite this as 2x over 4 plus x squared plus 1 over 4 plus x squared. And just deal with each piece of that separately. So for the first part, we're going to let u equal 4 plus x squared. Du will be 2x dx. And so we've got integral of du over u. And then for this one, we're going to use something similar to that very first one we did, where we factor the 4 out that was inside the square root. We'll do the same thing here. So if I take a 4 out of that, that's 4 times 1 plus x squared over 4. And I can pull that 4 that's in the denominator out to the front of my integral. So 1/4 of the integral of 1 plus x over 2 squared dx. And so for this piece of it, we'll just let u equal x over 2. And then du will be 1/2 dx. And we've already got part of the 1/2 there. We got a 1/4 there. So we break that down into a half times a half and clear out one of the halves. So we've now got natural log absolute value u from this one. Let's call those v's instead of u's in the second one, just so we don't confuse ourselves. So natural log absolute value of u plus 1/2 the integral of, and so our 1/2 dx becomes our dv over 1 plus v squared. So we got natural log absolute value of 4 plus x squared plus 1/2, and then this integral is inverse tangent of v, and v was x over 2 plus our constant. So, and they cleared off the absolute values on this because 4 is positive and x squared is always positive, so the absolute value is redundant. So it looks like that's choice D. Everybody good there? Any questions on 64? Why did I split it into 2? I split it into 2 just because I noticed that if I let u equal x squared plus 4, du could be 2x dx, but I don't have 2x, I have 2x plus 1 dx. And so if I split it into the two, I can deal with all of this and get myself a simpler integral as the rest of it to deal with. That makes this one very easy to do. And then this one just requires a little bit of factoring to make it into an inverse tangent. And that's the reason why. Does that make sense? I wouldn't expect you to have to do that, honestly, on the AP test. Most of the challenge ones in here are more difficult than what you'll see. And in fact, those ones don't say they're BC only, and they're, technically it's not, because you could find out how to do that, but normally we don't talk about splitting these integrals like this until you take BC. But, until you take Math 150, 151. All right, next one. Let's see here. That was 64, right? Okay. 33 is our next one here. Okay, so looking at 33, we've got the integral of sine 2x over the square root of 1 plus cosine squared x dx. Okay. There's probably a couple different ways to go about this one, but the best way that I see offhand is to just do a u sub for the thing inside the square root, as we often do. The derivative then is 2 cosine x times the derivative of cosine, which is negative sine x dx. Well, negative 2 sine x cosine x. If I forget about the negative for a second, 2 sine x cosine x is just sine 2x. That's the double angle identity for sine. So this is negative sine 2x. So all I need is a negative and a negative. And this becomes negative du over root u. Integral of root u, that's just u to the negative 1/2. So that becomes u to the 1/2, and you divide by the 1/2. So you end up with negative 2 root u plus your constant, or negative 2 root 1 plus cosine squared x plus your constant. Which, oh, now I'm looking at the wrong problem, which is choice A. I was looking at number 30. I was like, that's not the answer choices. That's choice A for 33. Any questions there on 33? All right, next one we got here is 38. And my pen is not working. There we go. 38. We got an integral of sine 2 theta cosine theta d theta. So we're just going to use the double angle identity on this one to turn sine 2 theta into 2 sine theta cosine theta times cosine theta d theta, which can be 2 times the integral of sine theta cosine squared theta d theta. And if we let u equal cosine theta, du will be negative sine theta d theta. Put in our negative and our negative. And we've got negative 2 integrals of u squared du, or negative 2/3 u cubed plus c, with u equal to cosine, so negative 2/3 cosine cubed theta plus c, which looks like choice A. I feel like a lot of these are A. Don't read anything into that. Any questions there on 38? right, 39 is the next one someone asked for. So 39, we got sine of 2t over 1 minus cosine 2t dt. This one's just another u sub. So we notice that the derivative of the denominator is very similar to the numerator. So we'll let du equal 1 minus cosine 2t. Sorry, not du, u. And du will be the derivative of that. The derivative of the 1 goes away. Derivative of negative cosine 2t becomes positive 2 sine 2t. And all we need then is a 2 and a 1/2. And we've got 1/2 of du over u, or 1/2 natural log absolute value u, plus our constant, which looks like choice C. So this is a 1/2 out in front of a natural log, so we can just go in and put that in as a power of 1/2 of the thing that we've got inside there. So they've rewritten it this way. Power of 1/2 is a square root. Everybody good there with 39? Any questions on 39? All right, next one is 58. No, we already did 58. Okay, next one is 77. All right, 77 says the equation of the curve whose slope at the point xy is x squared minus 2. So the slope is x squared minus 2, and it has to contain the point 1, -3. And so first thing we'll do is we'll just integrate. We'll get y equals x cubed over 3 minus 2x plus some constant. And then we will plug in our 1 for x and our -3 for y to find our constant. And what do we get? We get -3 plus 2 is -1, minus that is -4/3 for our constant. So it should be y equals x cubed over 3 minus 2x minus 4/3, which looks like that's choice D. Everybody good there with 77? Any questions on 77? All right, next one is 79. So 79 says find the acceleration needed to bring a particle moving with a velocity of 75 feet per second to a stop in 5 seconds. Okay. So if we know that dv dt is our acceleration, right? A derivative of our velocity is acceleration. So that means that our velocity function at any given time should be equal to the integral of a, right? Which is a times t plus some constant. And we know that our velocity is 75. When our t value is 0. That's where we're starting off at. So 0 plus c, so we get a constant of 75. And so we know that our velocity should be AT plus 75. And if we want our velocity to become 0, then we just need to, in 5 seconds, we just need to make this 0 equals 5a plus 75, or a equals negative 15. And I don't know if they had units on there, feet per second squared. Yep, negative 15 feet per second squared. Choice C. Any questions there on 79? All right. Next one we got is 16, back towards the beginning here. 16, we got the integral of 2x plus 1 over 2x dx. So this is one where if we've got a rational function and the denominator is just a single term here, we can just divide. So this becomes the integral of 1 plus 1 over 2x dx. And the integral of 1 is x. And the integral of 1 over 2x, well, that's just a half of 1 over x. So that'd be plus 1/2 natural log absolute value of x plus our constant. And just a real quick side note on this one, somebody in last period asked me to do this one, second period, and they said, well, we did a u substitution with u equal to 2x for that piece of it. So they had x plus the integral of u is 2x, du is 2 dx. So they had to put in a 2 dx over 2x with a 1/2. Well, if you do it that way, you probably note that, first of all, you could just cancel those 2's, and then it's just dx over x, and you don't even need to bother with the u substitution. But if you didn't see that, if you do the u substitution, you get x plus 1/2 natural log absolute value u, right? This is x plus 1/2 of du over u. So 1/2 natural log absolute value u, which is 2x plus a constant, which looks different than the answer that we got, which is what the answer choice was. But this is the same as x plus 1/2 of natural log 2 plus natural log absolute value x plus a constant, right? Because if I'm multiplying two things inside a logarithm, I can separate them into two different logarithms using addition. And this then is x plus 1/2 natural log 2 plus 1/2 natural log absolute value x plus a constant. Well, I still have the x, and I still have the 1/2 natural log of x, and a constant plus another constant is still just a constant. So the constant you get if you do it this way is different than the constant you get if you do it this way, but they're still constants, and so they effectively don't alter your answer at all. Everybody sort of see that? It's kind of an interesting thing to note there. Any questions there on 16? Cool. You guys are real talkative here. 23. Did we do 23 yet? I think I did this one already. Maybe it must have been last period. Okay, 23. So 23, we're looking at the integral of sine theta cosine theta d theta. There's really 3 good ways to go about this one. And it doesn't really matter which you choose, except that there's a bunch of different answer choices there. And so you kind of got to just hope you chose the right way. We're going to choose the wrong way twice and then choose the right way, just to see all the different ways to do it. So the first is let u equal sine theta and du is cosine theta d theta. This will give us a perfectly legitimate answer, but it doesn't happen to be one of our answer choices. So this just becomes the integral of u du. which is u squared over 2 plus our constant, or sine squared theta over 2 plus our constant, which is not any of our answer choices. We could use some Pythagorean trig identities to turn this into one of our answer choices, but we're not going to bother with that right now. We could also do an integral of sine theta cosine theta by letting u equal cosine theta, so that du was negative sine theta d theta. We have to put in negatives, which would give us the opposite of the integral of u du, or negative u squared over 2 plus a constant, or negative, this time, cosine squared theta over 2 plus a constant, which again, not one of our answer choices. We could use some Pythagorean identities to turn it into one of them, but we're not going to bother with that right now. The other thing we could have done is recognize that the integral of sine theta cosine theta is the same as the integral of, or 1/2 the integral of 2 sine theta cosine theta d theta. And 2 sine theta cosine theta, as we talked about just a bit ago, we should know that's the double angle identity. And then you can let u equal 2 theta, and then du is 2 d theta. And so you'll put in a 2, and you'll put in another 1/2, and you've got 1/4 the integral of sine u du. And the integral of sine is negative cosine, so you got negative 1/4 cosine u, which was cosine 2 theta, plus your constant. And that one is there as choice B. So 3 different ways to integrate that. Only one of them really gives us the nice answer that we're looking for. Any questions there on 23? All right, next one is 32. I think I did 32 already, right? Yeah. All right, next one after 32 is 34. Um, 34, what do we have? We got secant to the 3/2 power of x times tangent x dx. And then so for that one, it's probably going to be best for us. We could try and do like u equal tangent and du is secant squared, but we don't have a secant squared there. If we let u be secant, we'd only have a 1/2 power of secant left over for our du, and we would need a secant tangent, so we'd be a little short there. So if we rewrite this one in terms of sines and cosines, it might make it a little bit easier. So let's rewrite this as sine x dx from the tangent x over, this is cosine to the 3/2 in the denominator, and this is cosine to the first. So that'd be cosine to the 5/2 x in the denominator. And from there, if we just let u equal cosine x, then du ought to be negative sine x dx. Put in our negatives. We get negative integral of u to the negative 5/2 du. U, the negative 5/2 should go up to be negative 3/2. We'll divide by negative 3/2, which will cancel with the negative and flip to become 2/3. So we'll have 2/3 of u to the negative 3/2. So we'll put that in the denominator plus our c, which looks like, yeah, that's the secant. Yeah, so we got 2/3 secant to the 3/2 x plus c, choice D. They wrote it as secant instead of cosine in the denominator. Any questions there on 34? All right, next one is 39. No, we already did 39. Skip that one for now. Next one is 58. I think we did 58 already too, didn't we? Yeah. All right, I'm done 58. Then I'm 39 again. Somebody asked, we got that one already. All right, 70. 70. We've got, what do we got? We've got an integral of dx over 1 minus e to the x, which looks a bit complicated, right? There's no, doesn't seemingly be an easy way to go about this one. Remember there's a 1 up here. And I've kind of got to be a little creative with this one too. If I were to rewrite this, and I wouldn't expect any of you to have to do this on the AP test. This one's, I mean, yeah, they say it's a challenge problem. It's a little more difficult than I would expect for you to see on the AP test for sure. If you take the numerator and rewrite it as 1 minus e to the x plus e to the x over 1 minus e to the x dx. Nothing wrong with that, right? I have 1 up there, 1 minus e to the x plus e to the x. That all just goes away if I want it to. Those are equivalent. But then what I'm going to do is I'm going to take this piece of the fraction and this piece of the fraction and write them as 2 separate integrals. So 1 minus e to the x over 1 minus e to the x is just 1. And then this is e to the x over 1 minus e to the x dx. And the 1 minus e to the x in this one we're going to substitute out, because now in the numerator we've got an e to the x, and we need a negative e to the x, so we'll just put in a negative and a negative. Okay. But that's easy enough to solve and deal with. So this just becomes x, and then this is a minus, and now this is an integral of du over u. So we got x minus natural log absolute value 1 minus e to the x plus your constant, which is choice B, it looks like. Any questions there on 70? Okay. Next one I got here is 33. And 33 we already did, I think, didn't we? We did 33, yeah. Okay. Next one after 33 is 26. All right, 26, we're looking at an integral of cosine squared 2x. So in order to integrate cosine squared, if there's nothing else attached to it to do any substitutions or anything, we're going to have to use the half angle formula. And so half angle formula for cosine squared of u is 1/2 of 1 plus cosine of 2u, so that'd be 1 plus cosine 4x dx. Now we can just integrate 1/2, and then the integral of 1 is x, and then this one is a simple u sub. U is 4x, so du is 4. Put the 4 inside, which goes away. Put the 1/4 outside, so you get 1/4 sine 4x plus your constant. And my guess is they simplified that down a bit. Yeah, so probably 1/2 x plus 1/8 sine 4x plus your constant, which looks like choice A. Any questions there on 26? All right, we got 36. I know we're sort of running out of time here, but we're almost to the end of the list of ones people gave me, so I'll try and hang for a minute or two past, and then we'll get through them all today. So dx over sine squared 2x, or just leave as somebody just did. That's fine too. Okay, so for 36, if we're looking at 36, we're going to rewrite this for sure as just an integral of cosecant squared 2x dx, because we should know how to use, we should know how to integrate cosecant. An integral of cosecant is negative cotangent. And so that just is a simple u sub with u equal to 2x. So we'll end up with a 1/2 the integral of cosecant squared 2x times 2 dx, u equal to 2x, and du is 2 dx. So we'll end up with 1/2, and then the integral of cosecant squared, like we just said, is negative cotangent, so negative 1/2 cotangent 2x plus your constant, which looks like that's choice C. Any questions there on 36? All right, we got 2 more problems here. Next one should be quick, and I haven't looked at what the other one is. So, 37, we got inverse tangent of y over 1 plus y squared dy. So this is just a u sub. This is u equals, this one is what I hope you guys would recognize. U equals inverse tangent y. Derivative of inverse tangent y is 1 over 1 plus y squared dy. So this just becomes u du, which is u squared over 2 plus your constant, or inverse tangent x squared over 2 plus your constant. Or sorry, not x, inverse tangent y. Okay, all those y. And then the last one we've got here is 26, which we just did a minute ago. So it looks like that's all of them. Anybody have any other quick questions on any of that?